Namely, I generated the data, I transferred it to the model using something of this form. You can even do better by letting this U, which is a set of positive numbers at every time at which you're looking at the circuit, not dictated to you by any equations of motion, but letting it be a set of parameters that can be big where the circuit is very unstable and small where the circuit is stable. Because nonlinear circuits, nonlinear dynamical systems, aren't uniformly unstable over everywhere that they move around. Sometimes they're stable, sometimes they're not. So what I'm going to do is calculate this cost function again in a slightly different way. Instead of minimizing the cost function with U just a fixed number, I'm going to let U be a set of parameters. There could be 1,000 of them if I make 1,000 measurements. It's no big deal to minimize something with 1,000 terms. I'm going to minimize the difference between the data and the model output plus a penalty for how strong I have to push the system in order to make Y go to X. And what I'm going to plot for you is the minimization of this cost function subject to these equations of motion, printing out Y1, Y2, and Y3, which are being estimated. I will show you the final parameters that are estimated, and I'll show you U at every step of that minimization. And what we'll see is that sometimes it's big, in regions it's unstable, sometimes it's small. And when I'm all done, U will be 0, and I will be describing not this fake system in which I've coupled something in, but the original system that I'm interested in. And I will then know about my transistor. Building the K computer follow-up with my transistor might be a little harder, and I suspect that RIKEN will get there first, but you have to know there's competition, right? I'm up at 1 transistor, not even 1 CPU, okay? I wouldn't worry too much about the competition. All right, the minimization is an iterative process. We use a numerical program from the public domain, and what you have to do is give it a starting point. It cycles through and gives you an answer, and then it says, do you want to continue? And by do you want to continue, you give it a size which you want that cost function to be. Do you want it to be 10 to the minus 9th? Fine. You have to keep cycling. And we do that not only with the properties of the model, the voltages and currents, but also with this nudging factor called U. And here's what it looks like. This is the final answer after everything has completed and we've gotten an answer. I think this was asked to be correct to a part in 10 to the 4th. Here are the original parameters that we put into the model. Here are the estimates that came out of that procedure. Here are the voltages and currents out of the model. Here's the nudging factor, and here are the data that we've been given. And you can see that when we get out here in time, U has pretty much gone to 0. I'll show you a blow up of that. And all of the variables, including the ones we didn't measure, are properly estimated. Why should this system estimate the things we didn't measure? That's a question to you. I'm sorry, it's not a rhetorical question.
In a sense, you did measure it, because when you perform a measure with the system, it gives the answer thanks to the parameters that defines it.
Well, it's the parameters as well as the structure, architectural structure. And that's exactly right, and that's a feature of nonlinear systems. Everything is coupled to everything else. The atmosphere is not linear. If it were linear, all sorts of things wouldn't happen. I mean, we'd have all sorts of boring hurricanes, for example. But my point is that in a linear system, you sometimes can actually decouple parts of the system by partial diagonalization of the underlying operators, which are linear. In a nonlinear system, that's generally impossible. So by measuring one part of the system, you automatically stimulate and forced to act the other parts of the system, so that by measuring, in this case, one variable, I've estimated all three of them. So ask yourself while I talk, how many variables do you have to measure? Everybody, Eugenia, other people said, well, in our system we have 10 to the 9th variables. That's an appallingly large number, but if you want that kind of resolution in space, you need all of those variables. How many variables do you have to measure? Do you have enough? If you don't, the surface on which you search looks like that horrible surface I showed you. Here, the answer happens to be 1. In the case of most neurons, the answer is 1 because of the structure of the equations. And in the Lorentz 96 equations, which you exercised yourself on yesterday, the answer depends on the dimension of the system. In the Lorentz 63 equations, the answer is 1, but you better choose the right one because one of them doesn't help you at all. All right. It was interesting to us whether or not this way of transferring information from the data into the model could also track changing parameters in the model. So we took the parameter that drives the system, the voltage across the circuit that tells you how much the current is going through the system and driving it into oscillation, and we changed that over a period of time from about 5, where we knew the system would be chaotic. We made it lower than that. We made it bigger than that. We did this by hand. And then we asked, how accurately can the procedure I just described estimate the changing in that parameter? The behavior here is periodic. The behavior here is chaotic. So you're asking it to really work hard to capture the motion in phase space as you change the nature of that motion. And here's what you get for our calculations. This is numerical. This is not experimental. Now I think we're ready for the experiment. Oh no, I wanted to show you what happened as you go through the iterations. All right, I gave you the system. I gave you some data. And I said, march on, but you have to start somewhere and iterate until the data and the model voltage are close to each other. Well, generally, you have no idea where to start, so you start in an arbitrary place, and you let the optimization procedure, the data assimilation procedure, through this coupling, operate. So after 6 iterations, you can see you're not doing very well. And furthermore, if you look at how big that nudging parameter is, you can see over the period during which you're making the observations, that nudging parameter can be big and it can be very small. And that says that the nonlinear system you're talking about is very unstable here, and it's working really hard to overcome that instability. And it's very stable in this region. You don't need this extra little push. Yes, sir?
I was just seeing the plots from this slide and as well as the previous slide regarding the transient behavior of the circuit. So it is something different. It's looking near to 0. So all of this, what we are discussing is an asymptotic regime, right?
No.
Okay. So
No. Well, it's asymptotic in what? I have to guess a set of numbers which are the initial conditions for the differential equations. I have to guess a current at time 0, a voltage at time 0, and the other voltage. Those are surely wrong. But then I solve the equations from those initial conditions, and I get an output voltage after some finite time. I also have to put in a set of numbers which tell me how strongly to push the output of the model towards the data. And I believe in this case, we chose them all to be 5 at t equals 0. And then we said, keep going until the error of the accuracy of the model relative to the accuracy of your data is 10 to the minus 5 in some units, some dimensionless units, okay?
So we are not taking care of transient
Well, when I get to the last picture, which took 260 operations in which it said, all right, I got to 10 to the minus fifth. I'm finished. Is that OK? And you're supposed to say yes, because that took 5 minutes in this case. OK? All right? So this is what happened after 6 iterations. It's not done. This is what happened after 22 operations. You can see that it's beginning in some of the state variables to match their value, including their value at t equals 0. So the transients in time are matched by this as well. You're matching over the whole observation interval. What you care about eventually is what happens at the end. You want that to be as accurately matched as possible so that the predictions you make are accurately matched. But we're not there yet. Right now we're fitting. OK? All right. How big is the nudging parameter? Well, you can see it got smaller because we got closer. And so I didn't have to come in, and you can think about this as a control operation if you like. You didn't have to come in and push the system really hard as earlier, because you were getting close to x equal y. And so the coefficient of it didn't have to be quite as big. Keep running. And after 246 iterations, with this particular public domain optimizer in this particular system, it said, I'm done. I've shown you what the parameters were like. I'm showing you how accurately it matched the output of all of the model parameters, model states, to the ones that we knew, because this was a numerical experiment. And finally, how big do you think the nudging factor is?
Close to 0.
Pardon me?
Close to 0.
Yes. It's actually 10 to the minus 13th, which is machine accuracy for this laptop computer. And it could never be smaller than that in this program. If we did it triple precision, it might get down to 10 to the minus 20th, but that's a fake. It's 0. And that's great. The forcing that you put in by hand to help you transfer the information's gone. All right. That was numerical. Then we spent our $10. We built the circuit. And this is an example of where we measured the voltage. Let me, since you don't know what transistors look like. We measured the voltage between the base, which is where the electrons are injected, and the voltage of the emitter to which the electrons took a path and then entered the circuit. So this voltage was measured. We want to determine the current across the inductor and the voltage across this pair of leads in the transistor. So this is the result of our going through that procedure. I'm not going to show you all the details again. I showed you it in the simulation. But this is measured. This is an unmeasured variable and another unmeasured variable. I'm very glad to see it's not perfect, because I could hardly face you and pretend to you that it was a perfect estimation procedure.
So BCE and IM is just opposite in phase, right?
Not quite just opposite in phase. It's close, okay? But they're not exactly opposite in phase, all right? But I have to admit, you have to have a little bit of imagination to get this little bump to match that little bump. But you don't need any imagination to see that that dip matches that bump, okay? This is what you get. Now, the real test of this is not that I got a good fit for the thing I measured. If I didn't have the privilege of looking inside the transistor, I wouldn't know how to make these plots, because I didn't measure those things. What I care about is the estimation at the end of my observation window, where I'm no longer taking any data, but I now predict how the system will evolve in time. So I'm going to take the estimated parameters and the estimated state variables, measured and unmeasured at this time, and calculate forward using my model with k equals 0, because I'm no longer transferring any information. So I'm saying, whoops, what happened to my picture? Yeah, there it is. All right, so this is the end of the observation window, and this is a prediction window. And you can see that I do very well until, because this is a chaotic system, and I don't estimate to 1 part in 10 to the minus 97 or other impossible accuracies. There's small differences between this and what the device was actually doing. So in comparing, eventually they differ because the system is unstable and chaotic. If this didn't happen, you got the wrong answer. If this were the atmosphere, which I admit it is simpler than, and I estimated the state of the system before I made a prediction, it would tell me, as we already know, that I have to go out and measure again to re-estimate the state of the atmosphere because it was chaotic, and the small errors that I made the first time around got amplified. Okay?